Alright, greetings class. Today we're going to talk about lesson 13, which is on inverse functions. And this one shouldn't be too bad, I don't think. It's going to combine a couple things we've looked at. So if we have two functions, let's say f of x and g of x, we say that one is the inverse of the other if when I plug one into the other I get x out. Okay, so I would say f and g are inverses. Okay, if when we plug g in to f, right, so f of g of x, we get out x. Alright, or the other way around, if I plug f into g, I get x. Alright, so that's the definition, and we usually use this notation. The inverse of f of x we call, and it's going to look a little odd, it's f to the negative 1. We use this to represent the inverse function of f. Alright, we've already seen inverses before. We might not have called it that, but for example, the cubed root is an inverse of a cube, right? Because when we take the cubed root of x cubed, these cancel and we get out x. Or if we take the cubed root of x and we cube it, they cancel and we get out x. Okay, so we've already seen inverse functions before, this cancellation idea. It's just inverses. So in the same respect, the square root of x is an inverse of x squared, provided x is greater than or equal to 0. Okay, we got to be careful there, and we'll get into details in a second why that is, but we didn't need that restriction up here, but it has to do with the fact that I can't put negatives underneath the square root of x, right? That's kind of where this issue comes from. But basically, if I take the square root of x squared, the square root and the square cancel and gives me x, and this is provided x is greater than or equal to 0. And if I take the square root of x and then square it, we get out x. Okay, so we've been dealing with inverses for a while now. We just didn't realize it. Alright, in fact, how we've been solving equations is basically getting that weird thing off to the other side and then applying the inverse. Alright? Okay, so finding inverses basically means we're going to be swapping x and y. Right? We flip our x and y. So if our function, we're going from x to y via f, right? F takes x and gives us a y value. To go back the other direction, that's going to be our inverse. Now, the thing we need to make sure about is when we flip around that we still have a function. Okay, so remember, to be a function, every input can only go to a single output, right? So basically, if I have 1, 2, 3, and these are going to 2, 4, 9, right, this is a function because every one input, every x only goes to a single y. In order to map this back, right, so if we map backwards, so now I make a new function. So if this was f, let's call this f inverse that we're making now, and I want to map all these back. Okay, say I want to take 2 now to 1, 4 to 2, and 9 to 3, this is still a function, okay? Because each individual x now only goes to a single y. But if, for example, I had this function, let's say, let's call this g. All right, let's say g takes -1 to 1, 0 to 0, 1 to 1. Okay, like that. If I try to map it back, so this is actually a function because each x goes to only a single y. But if I try to map it backwards with a g inverse, so say I'm mapping this around, so 1 would go to -1, 0 would go to 0, but then now I have 1 going to +1. So this would not be a function. Okay, I could have just said not a function instead of not be a function. Okay. So this is not a function when we map it around. So when we're trying to find inverses by swapping the direction of each function, we have to be careful that no x's map, or I'm sorry, no y's are counted more than once. So what this means is that we're looking for functions that are 1 to 1. Alright, so this basically tells us that we can only find inverses for functions that are 1 to 1. And that's what we call it. And that basically means that each x goes to 1 and only one y. Meaning that x, basically that the y's can't repeat it, or be repeated. So graphically, okay, a 1-to-1 function is both a function, so it passes the horizontal, it passes the vertical line test, that we talked about previously, and the horizontal line test. Okay, let's consider this function here. This is our f of x. This is not 1-to-1. It's a function because it passes the vertical line test. Every vertical line I draw only crosses the graph once, but it is not 1-to-1. Okay, because pretty much any horizontal line I draw crosses the graph twice. So I'll say this fails the horizontal line test. If it's not 1-to-1, that means it does not have an inverse function. But hold on. This looks like x squared. In fact, x squared looks like a u right here stemming from the origin. Right? This is x squared. And we said that provided x is greater than or equal to 0, that the inverse for f would be the square root of x. Alright, now here's where this greater than or equal to 0 thing comes in. If I just ignore the negative side of this u, okay, not only do we pass the vertical line test, but we pass the horizontal line test too if we restrict our domain to just the positive x's. Okay, so x squared is not 1-to-1, unless we restrict the domain. Okay. Once we restrict the domain, we can find an inverse just on that restricted domain. Okay, so meaning it doesn't have an inverse everywhere, but it will have an inverse from x equals 0 to infinity. Okay, but let me say, so x squared is 1 to 1 on 0 to infinity, so it has an inverse on 0 to infinity. Okay, so when we find an inverse for that, and a lot of times you'll see that in these problems that MyLabs Plus gives you, it will restrict the domain for some of them. It'll say, you know, find the inverse provided x is greater than 0, or x is less than 14, or x is, you know, between these two values. Okay, given this function, this is actually going to be 1 to 1, and it should have an inverse everywhere. This is our f of x. It passes the vertical line test as far as we can see, and it also passes the horizontal line test, because every horizontal line I draw, any vertical line I draw, only crosses the graph once, only once. So this is a function, and 1 to 1. Therefore, this function has an inverse. This function, on the other hand, I can tell it's a function because it will pass the vertical line test, but it does not pass the horizontal line test, and the axis itself acts as a horizontal line where it fails. It crosses 3 times. So this is not 1 to 1. So we can't find a nice inverse likely. Maybe if we restricted the domain just from here on, we could, or maybe here through the negatives, or maybe just in this little spot. So we could, if we restrict the domain, kind of we'd have to be kind of fierce about how we restrict the domain, but if we did, we could find an inverse on just that restricted domain. But as is, overall, we can't. So it's not 1 to 1, so no complete inverse, I'll say. All right, let's talk a little bit about finding inverses. To find an inverse, as I said, it's all about swapping x and y. Now in this case we don't really have a y, so what we'll do is we'll put in a y, so that we have y is equal to 2x plus 3, because we know that those are interchangeable, and then we can swap them. Now the order here is a little, I won't say it's not important, it can be depending on the cases you have, but I like to solve for x first and then swap, but you can swap and then solve for y instead. How you want to do this is really up to you. So what we'll do here is we'll swap x and y. Okay, so we swap our x and y. So I get x is equal to 2y plus 3, and then we'll solve for y. Alright. Now, what we're going to do, we're going to move that 3 over and get x minus 3 is equal to 2y, and then we'll divide both sides by 2. Okay, so what we have is x minus 3 all over 2 is equal to y. Once we solve for y, this, on this side here, this x minus 3 all over 2, is our inverse function. So f inverse of x is equal to x minus 3 over 2. Okay, now I didn't mention whether or not this original function was 1-to-1. It is. Okay, so this is 1-to-1. We're going to look at it in just a second. Okay. All right. Cool. Okay, now how could we check this? We found it, and if we go back to our original, right, the original definition is that if I plug one into the other, right, so if I take, say, f of x and I plug in f inverse of x, we should get out x. Okay, so if I take this f inverse function and plug it in, x minus 3 all over 2, into f, we should get everything canceling out to give us x. Okay, so if I swing back up here to my function f of x, I have 2x plus 3. Okay, so what this does is going to take 2 times whatever's in here, which is x minus 3 all over 2, and then it's going to add 3. Okay. Alright, so the 2's cancel, and we get an x minus 3 plus a 3. Now the 3's cancel, and we get an x. And there we go. Alright, so that is how we check it. We could also do it the other way. So over here, let me do f inverse of f of x. Okay. So that would be f inverse of f of x was 2x plus 3. So I'm doing that off to the side here. Okay, and f inverse, what did it do? It put x up here, subtracted 3, then divided the whole thing by 2. So we're going to take 2x plus 3, subtract 3, divide the whole thing by 2. And we see here, 2x plus 3 minus 3, those minus 3's cancel, so I get 2x over 2, the 2's cancel, and we get x. So in both cases, plugging in one function into the other, everything cancels out, and we get out x. Okay, I wanted to look at another example real quick, just to show something that would be easier to graph when we do this. So let's find the inverse here. This is 1-to-1. And if you think about y, that's a line. Its slope is 4. Its y-intercept is -8. Not too shabby. We're going to let y equal this 4x minus 8. And last time I mentioned we swapped x and y, and then we solved for y, right? We did it in this order. We swapped x and y, then we solved for y. Well, I'm going to do it in the opposite order now. I'm going to instead solve for x, which this way is kind of nice because we're used to solving for x more so than we are solving for y, right? We're going to solve for x and then swap once we're finished. Okay? So we're going to start by adding 8 to both sides. So I get y plus 8 is equal to 4x. And then I'm going to divide everything by 4. Okay? So on this side, when I divide everything by 4, right, it cancels here. I have y plus 8 over 4 is equal to x. What I'm going to do is distribute this. So instead of doing it as a whole fraction, I'll do y over 4 plus 8 over 4 is equal to x. Right? And this I can think of as 1/4 y plus 8 over 4 is 2. Okay? And now I'm going to swap x and y. Right? Now when I swap x and y, I'll get 1/4 x plus 2 is equal to y. And this is my f inverse. Okay, so f inverse of x is 1/4 x plus 2. Alright, so here's the thing. It actually doesn't really matter which order you tackle this in. You know, whether you solve for x then swap, or swap then solve for y. As long as you swap at some point. Okay? I like doing it this way, and it's hard for me to actually tell you why until we get to an example where it comes up. But when it does, I'll be sure to point it out. Okay, so let's actually graph these and see what happens. Okay, so here's my axis that I've started. I'm going to graph this first function here, f of x, which is 4x minus 8. So we have a y-intercept of -8 and a slope of 4. So when we go over 1, we go up 4. So 1, 2, 3, 4. And over 1, 1, 2, 3, 4. Okay, so we have this line here. Okay, so this is the function f of x is equal to 4x minus 8. Okay. Next up was 1/4 x plus 2. Okay, so our y-intercept there was 2. 2. And our slope was 1/4. So we have 1/4. So when we go out 4, 1, 2, 3, 4, we go up 1. So it looks like I didn't graph this super well, but it looks like I've got something like this going on. Okay. Now, graphs of inverses, so the second one was f inverse, which is 1/4 x plus 2. What they do is they are balanced. Let me use a different color here. Let me use red. They are balanced or mirror images of one another across the line y equals x. Okay, so whenever you graph them, you're going to see that they mirror each other. They flip around this line here, y equals x. And that will be easier to see when we start looking at more complicated examples, but I wanted to show you just from the graph that I threw together here, not very well, but that inverses flip around the line y equals x, which makes sense because to get from one to the other, what am I doing? I'm swapping y and x. Therefore, the graphs should swap y and x, so they should almost look the same except flipped around this line y equals x. Okay, next up, let's look at f of x is equal to the cube root of x minus 2. Well, this function is 1 to 1. We'll look at a graph of it in just a second. And actually, it's a little weird how they do this, because in the next section or so, we'll talk a little bit about how we know what these certain graphs look like. But in any case, here we are, taking it on faith that the cubed root of x minus 2 is 1 to 1. Okay, so we want to find f inverse. Okay, so to do that, remember we put a y in for our f of x. And we can either swap x and y, or we can just solve and then swap later. So first, I'll just solve for x to start with instead of process swapping, or actually, you know what, just to shake it up each time, let's do it differently each time. So here I'll swap x and y, because it, again, in the next example you'll see why I like to do it the other way, but in this one it's not really going to matter that much because our function's 1 to 1. Alright, so when I swap x and y, I'm now going to get x is equal to the cubed root of y minus 2, and now we're going to solve for y. Again, another reason why I prefer the other way, I'm more used to solving for x than solving for y, but in any case, I have the cubed root of some stuff here on this side. Let's think about how we would go about solving that. I'll give you a minute to think about it before I just give it to you. Okay, and yeah, we're going to cube both sides. Okay, so x cubed will be equal to the cubed root of y minus 2 all cubed. And so the cubed root and the cube cancel, and so we get x cubed is equal to y minus 2. Alright, now to finish this off, solving for y, I'm just going to move this 2 over. So x cubed plus 2 is equal to y. So this is going to be our inverse function. Okay, so f inverse is equal to x cubed plus 2. Alright. One thing I want to show about these two functions, what does f do? F takes x, subtracts 2, and then takes the cubed root of the entire thing. F inverse takes the cubed root of x and then adds 2. What I think is the thing to notice here is that inverses do the opposite operations in an opposite order. This one starts with a subtraction, then does a cubed root. Okay, then this one, it changes that subtraction to addition, and instead of taking a cubed root of everything, it just cubes the x. So it changes the operation. It gives the opposite operations. All right, we had a plus that goes from a minus that goes to a plus, a cubed root that goes to a cubed, and the order is a little different. Instead of cube rooting the entire thing, here we're just cubing part of it. All right, now to check, there are a few problems in the homework that actually ask you to check. You're just going to take f inverse and plug it into f. Okay, so f inverse was x cubed plus 2, so what we're doing is we're going to plug x cubed plus 2 into f. So what was f? F, if we look up here, it takes whatever's in parentheses, subtracts 2, and takes the cubed root of the whole thing. So this will be the cubed root of x cubed plus 2 minus 2. Okay, so basically whatever is here gets put here. So that's what I've done. I've taken this and stuck it in here. So we're going to subtract the 2's. Oh, so the 2's cancel. So we end up with a cubed root of x cubed, which cancel and give us an x. Okay. We can also do it the other way. If I do f inverse and plug f in, so f, remember, was this cubed root junk up here. So this is going to be f inverse of the cubed root of x minus 2. And what does f inverse do? F inverse cubes whatever's in parentheses. So it's going to take what's in parentheses here, it's going to cube it, and then, oh, we can see it up here in the corner, then it adds 2. So the cubed root of all this, the cubed root cubed cancels, I get x minus 2 plus 2. We that was checking. Now let's actually look at the graphs of these things. Okay, so to do that, what I'm going to do is go to my calculator. I'm going to go to my y equals. Okay, I'm going to start by graphing this first guy here. Now, if you don't know where the cubed root is, well, some calculators have a cubed root, some don't. What we're going to do is I'm just going to take this x minus 2 and instead raise it to the 1/3. Because remember, a cubed root is the same thing as a 1/3 power. Okay, make sure you put the 1/3 in parentheses. Then I'm going to do zoom 6, which puts it on a standard -10 to 10, -10 to 10. Okay, so there we go. I don't know if that's coming out very well, but we have that function. Alright, and it might serve us to change the way the y's are so we get a better view. But before I do that, let's graph the inverse function now. The inverse was x cubed plus 2, so that one's a little easier to do. Okay, and you can see that hopefully there. So here's our original function. Here's our inverse. Now, if I graph the line y equals x, check out what happens. We can see that the inverse and the original function are completely balanced across this line. In fact, they're mirror images of each other across the line y equals x. Now, some problems are going to ask you the domain and range of the inverse function. Now, here's a little trick. For this one, the domain, well, I know it's going to be negative infinity to infinity because nothing messes this up. Okay, but what is the range? Well, if we go back here, let's clear some of these out. Let's get rid of x and the original function and just look at the inverse function. And we see it seems to be in the y's going from negative infinity up to positive infinity. So we're going to get negative infinity to positive infinity. Okay, so this one's not that interesting. This original function, its domain and range were both all real numbers. The inverse's domain and range is going to be all real numbers. So nothing really special there, nothing really out of the ordinary. Okay, it's in the next example we see where things are going to start to get a little more interesting. Okay. Alright, for this next example, what we're going to look at is f of x equals x squared plus 4. And note, we are told that x is greater than or equal to 0. And there's a reason for that. If we graph this function, do on a graph real quick, but we see it's not 1-to-1, right? Every horizontal line I draw here pretty much will cross the function twice. So if we only restrict this function to when x is positive, we'll get something that's 1-to-1. Now if I want to see that, there are a couple ways we could do this actually. I don't want to get too bogged down. What I'll do is I'll just go to my window, and then my x-min I'll just let be 0. So I'm only looking at positive x's. Okay. Now I'm not going to ignore the negative y's just yet. We never know, but we may need to at some point. Actually, let me go ahead and do that. Let me get rid of the negative y. So I'll let my y-min go from 0 to 10. So now I'm just looking at quadrant 1 where everything's positive, both x and y. Okay. Now in this piece, it looks like the function is 1-to-1, so we can actually find an inverse. Now to do so, I'm going to let y be x squared plus 4, and here's why I like to not swap yet. I'm going to solve for x, okay, before swapping, and you'll see why. So I'm going to move this 4 over, so we'll subtract 4 on both sides, and get y minus 4 is equal to x squared. Okay? Now here's the thing where I think people mess up. Remember, if x squared is equal to something, that means x is equal to not just the square root of y minus 4, it's plus or minus the square root of y minus 4. Okay, plus or minus. Now here's where this is going to come in. So let me over here write it like this. X is plus or minus the square root y minus 4. What do I know about x? What am I told about x? Well, x is greater than or equal to 0. In other words, positive. It's non-negative. Okay? So, which one do I choose? Do I choose the positive square root or the negative square root? And the answer is, of course, the positive one. Because, now don't actually write that as your answer. If you were going to do this with a plus, my last plus will freak out and tell you you're wrong. But we're choosing the positive because I know we're restricting our domain to when x is greater than or equal to 0, so we choose the positive. And now I'll swap x and y. Okay, so if you wait to swap x and y, if you're told about x, it can help you choose things like this if you have a restricted domain. Okay, so that's really when the difference happens. Usually it doesn't make a difference, but if your domain is restricted, this can help you choose which one you need, a plus or minus. Okay. Just a little thing, a little heads up, a little rule of thumb that helps me. Okay, so now when I swap my x and y, okay, I get that y is equal to the square root of x minus 4. So my function f inverse of x, my inverse function, must be the square root of x minus 4. Okay, and we see similar patterns from before. Right here we went from an x squared plus 4, we changed the plus to a minus, we changed the square to a square root. Okay. Now we can check this to make sure if it's accurate, right? F of f inverse, if I plug f inverse into x, that would be plugging this square root of x minus 4 into f. Okay. And doing that, well, what does f do? It squares whatever in my x place and adds 4. So it's going to take this thing, square it, and add 4. Okay, so the square root and the square are going to cancel, so I get x minus 4 plus 4. All that junk cancels, and we get down to x, and there we go. Inverse matches. Or it satisfies what we want it to satisfy. Okay, maybe matching isn't the right word. Alright. Now, let's look at the graph. Alright, here's the graph of our original function. And let's go back to our y equals. You see I've put in the x squared plus 4. That's our original. X squared plus 4. Now we're going to put in square root of x minus 4. So square root of x minus 4. Okay. So there we go. We do have a square root here. It's right there. You don't already know. Hit graph, and there we are. There's our inverse function. Okay. It's, you notice that it's not a square. It's kind of a rectangle, so things don't look, don't quite look as balanced as maybe they should. Okay, but now I will graph my y equals x. Select that. I have that there from before. And as we can see, what we've done is we're taking this graph here and spinning it around the y equals x line. And they don't look that balanced just from, as I said, the window. So let me see if I can play with the window and get it to look a little more balanced. Because this is still 0 to 10, 0 to 10, but on a rectangle. So stay tuned. Okay, this isn't perfect, but you can see it a little better that they're balanced, their mirror images across the line y equals x. Okay, and if you go to the window, all I did is I changed the y from 0 to 8. Maybe 0 to 7 would even look better. Let's see. Maybe. Okay, just changing that y does, makes it look a little more balanced, considering we weren't on a nice square grid. Alright, but the point here is just to show that inverses and original functions balance across that y equals x line. There are some problems on the homework that ask you to check that out. Okay, before we move on to the next example, what I want to show is how we find the domain and the range. First, I want to look at my domain of our original function. Okay, and I'm going to change my window a little bit here. That's not what I meant to do. Okay. So remember, we restricted our domain so that x was greater than 0. So for our domain, our x's, let me give myself a little more y's to work with. Okay, my x's are going to basically go from 0 on. We can map this down. It's hard to see, but it just keeps on going. So our x's, our domain for our original function, okay, is 0 to infinity. That's the domain for f. The range, well, if we look at where the y's are, going from down to up, the function starts here at 4 and continues on up to positive infinity. Okay? But there's nothing going on here below 4. So the range is 4 to infinity. Let's look at our inverse function instead. Okay. So when I go to do the domain, so let's go down here for inverse, or actually, let's do it over here, next to our domain and range for f, for our inverse, our domain. Remember, that's our x's, so we have no function over here. It doesn't start until 4. 1, 2, 3, 4. And then it goes all the way out to infinity. So our domain is going to be 4 to infinity. Our range, on the other hand, well, the function doesn't exist in the negative, and if you really want to see that, if you do negative, say 5 to negative 10, we really see that there's no function down here. So it's basically 0, starts at 0, and then it goes on up, right? Because it continues to increase just slowly, right? So, and it might be easier to see that if you did negative 5 to 5, for example. Right? Maybe a little easier to see there. So the range for the inverse is 0 to infinity. Now check out how that compares to the domain and range for f. See that they are swapped, that the domain of one is the range of the other and vice versa. Well, that would make sense, right? Because the domain is your x's, your range is your y's, and what did you do to go from f to f inverse? You swapped them and So now the domain of f inverse was the range of f and vice versa. You swap them. So you swap the domain and the range. So basically the domain of f inverse is the range of f and vice versa. Thought that was just a little neat something to show y'all. Okay, let's look at another example. Alright, let's say we have f of x is equal to 2 over x. And the only restriction we have here is that x can't be 0. Okay. Alright. So I'm going to put my y in. And we can swap or we can start by solving. And if we have a fraction like this, here's the trick to solve an equation like this. So I'm going to just solve for x. Okay, so when you have x's in the denominator, what you can do is you can multiply everything by x. So we're going to multiply x, and when we do that, the x's here will cancel, so I get xy is equal to 2, and now I'm going to divide everything by y. Okay. So now I get x is over, or is equal to 2 over y. Well, that's okay, great, and now we swap. So we've solved for x. Now we're going to swap x and y, and what happens? We get y is equal to 2 over x. That's exactly what we started with. That's a little odd. Well, here's the thing. If this is my f inverse, if I plug f inverse into f, right, so that would be f of 2 over x. What does f do? Well, f takes whatever's in the x and divides it by 2. So I'm going to take 2 over x. Okay, well that's an odd function. I mean, I guess everything in here is even, but how I'm going to do this, whenever I divide by a fraction, remember we prefer to invert and multiply, so I'm going to invert this and change it to multiplication. So I'm going to have 2 times x over 2. And now the 2's cancel, and I'm left with x. Oh, interesting. So 2 over x happens to be its own inverse. In fact, any constant over x is its own inverse. These are the functions that are strangely their own inverse. That seems a little strange. What's going on with that? Well, let's take a look at the graph and see if we can figure anything out. Alright, here I have 2 over x, and I'm going to do a zoom 6 to give me a standard view. Okay, that's not maybe the best view. It's kind of hard to see the graph. So let me go from -5 to 5. Okay, here we go. Here's the graph of 2 over x from -5 to 5 on both axes. And you can kind of see it makes a swoopy thing. Okay. Alright, and if I graph this y equals x, notice I didn't put another 2 over x because it wouldn't do anything. But we see that the graph actually does look balanced across the line. In fact, if I go just to quadrant 1, okay, just in quadrant 1 we can see that across this line, and we're going to pretend like the window's a little better, but we basically flip this guy around, we do get its own inverse. We're basically taking the function itself, and when we flip it around, get a mapped function. Or in any case, a balanced function around the line y equals x. Okay? So that's one of the nice, interesting things out there. 1 over x, 2 over x, 3 over x, all those over x functions are going